Okay, welcome everybody. My name's Kieran. I'm one of the astronomy guides here. Thank you, Mickey. I'm one of the astronomy guides at the Dark Sky Project. And today we're going to talk about what we call the Magellanic clouds. As I like to say, the crown jewels of the southern night sky, because they're some of the most beautiful and amazing objects, I think, in our southern night sky. Very, very special. We'll talk about kind of what they are, what the importance they have in both the southern hemisphere and also in today's science and astronomy as well. So we'll get started with where they actually are in the sky, because I appreciate a lot of you guys are probably not from around here. Those of us that live here are quite used to them, but a lot of people are from the northern hemisphere, so it's a good idea to start with where they are. So the first thing is what we mean with the southern night sky. So roughly this is an area of the sky sort of around a spot above the South Pole. So if we look on the left here, to start with, this little orange man here would be standing on the South Pole exactly. So directly above his head in this little blue circle there would be what we call the southern night sky. So if you're in the northern hemisphere on the other side of this globe, you don't see that part at all. The Earth is in the way. So this is a kind of special, the part of the sky that's special to us. The rest of it, so where this kind of orangey circle is, that bit of the sky is seen all over the world. It's seen both in the north and the south. But we're not on the South Pole here, right? We're about halfway in between the South Pole and the equator. We're about 44 degrees south here, so pretty close to this diagram. So now the orange man is still on the South Pole, but we are here. No, that's the wrong way around. This is where we are with the orange man, and the South Pole is here, sorry. So for us, this blue circle is now tilted in the sky. So the spot directly above the South Pole is there, or 44 degrees up in the sky. But we can still draw this circle in the sky. We can still see the whole thing from here. So what I mean is, if we look now at this is more a picture of the whole sky as seen from here in New Zealand. So once again, our spot above the South Pole is here. That blue circle is now here. When we are seeing the parts of the sky that are shared across the world, that's more like this band here. So if any of you are from the northern hemisphere, we have some very famous constellations like Orion is here. The sun and the moon and the planets would move through sort of this part of the sky, that is, the sun moves through the northern sky here in the southern hemisphere. And so this is, again, that spot above, a special spot around the South Pole. And we see these are our two Magellanic clouds here and here, so they're quite close to that spot directly above the South Pole. I appreciate this map is a little confusing if you've not really seen the sky here before, so instead I've taken a picture. This is one of my pictures, actually. And this is pointing south. We can tell because we've got the beautiful aurora towards the south here. Once again, I've drawn this circle for us, the same circle we've seen before, and that spot above the South Pole would be about here. So for reference, the Southern Cross is found here, 1, 2, 3, 4. I know it's difficult in the picture, but that's where it is. And the two, what we call the two pointer stars, are here. We use to point to our Southern Cross. So this again is the two Magellanic clouds. So we call them clouds because they look a bit like clouds to your eye. So if it's a perfectly clear night, they're quite obvious in a dark sky area like right here. If there's real clouds in the sky, they can be quite hard to pick out because they do just look a lot like little clouds up there. So yeah, they are close to that spot above the South Pole. So that's where we can look for them in the sky, and we'll go and talk about the southern hemisphere here, because of course they're known to southern hemisphere cultures for a long time. So Australia, New Zealand, South America, parts of southern Africa, and a few other places as well. There is no history in the northern hemisphere before explorers start to come down into this part of the world. So they have very many names in various different cultures in the southern hemisphere, like very many names. Even just in New Zealand, they have at least a dozen different names for different Maori tribes. In Australia, the Aboriginal groups were spread all over the continent of Australia, and they each had their own stories and their own names as well. So we come up with a huge big list. I'm not going to go through them all, but we're going to go through some of the more interesting ones, I think. So to start with, we'll go with some of the New Zealand ones. This is just a small selection of them. Now here in this area in the South Island, the tribe that they call Ngāi Tahu, who we work with at the Dark Sky Project, they use the names I put at the top here. So Manukau Uri and Manukau Tia for the large and small Magellanic Cloud, respectively. And what was believed here is that they are pools of strength that are drawn on by one of a very important kind of figure in tradition and culture here they call Aotahi, which is a star, which is actually the second brightest star in the whole sky that we more normally know as Canopus these days, but they called Aotahi. And he was, as I say, one of the most important figures in Maori astronomy and being the second brightest star as well. So they believed that he drew strength from these two pools. Different Maori tribes came up with different ideas, and as I said, there's lots of different ideas. So we also have Australia. So to briefly go over that. Now, there's not a lot of art that survived. Oh no, I missed one. I missed a stage. I didn't put it in my notes. One of the other stories that is told more in the North Island that uses these Magellanic clouds. Now, they're a little faint here, but one of them's there and one of them's there, is what we call Te Waka o Tama Rareti. So, a waka is a canoe. And canoes are extremely important to the Maori because they're descended from Polynesian sailors and settlers. And these are peoples who sailed all over the Pacific Ocean, just across the open ocean, in essentially fairly small wooden canoes, which is a feat that not many other cultures throughout history managed at all. It's really hard to overstate just how impressive this really is. Before the advent of modern technology, almost nobody dared to go into the open ocean, who probably would not be coming back, because it's very hard to navigate across the open ocean. But nevertheless, the Polynesians did so for hundreds of years, or possibly longer, and traveled all the way from kind of Hawaii down to Aotearoa, New Zealand, across to Fiji, Samoa, and various other Pacific islands as well. And they did so in these canoes. So these canoes are incredibly important to them. This particular one, so they make a lot of canoes and shapes in the sky. This particular one is extremely large. It's so big that it really only appears for about an hour, because as the Earth turns, in the west, these ones go down and these ones rise. So because it's so large, taking up about a third of the sky, you only really get it for a short period of time. So the front of the canoe, the waka, is here. And this group of stars we usually know as Scorpio or Scorpius. This is the tail of the scorpion here. The anchor of the canoe is our Southern Cross, so 1, 2, 3, 4 stars of the cross, with the line of the anchor being our 2 pointer stars that we usually use to find the cross. Moving towards the back, the base of the canoe is found near the brightest star in the sky, Sirius, and then here we have Orion's belt, which makes up the back of the canoe. Our star Canopus, which was Aotahi as well, is the navigator in this canoe. It was probably one of the most important people in the waka to make sure that it didn't get lost at sea. And we make our mast up to this very bright star up here we call Achernar. And then our 2 Magellanic clouds are now sails of the waka. So they sit here and here. So kind of very important in this configuration, but that's only for a very short period of time, about an hour, maybe once or twice a year. So it's only briefly that the Maori consider these 2 part of that particular constellation. So now moving to Australia, there's kind of not a lot of representations that still survive. This is a bark painting that comes from Yirrkala culture, and they consider it to be a pair of sisters, so an older sister and a younger sister. The older sister being the large Magellanic cloud here, the younger sister being the small one, who each lived, considered like campsites where they lived with their dogs, which is nice. Other Aboriginal groups consider lots of different things. So we have pairs of animals, pairs of birds, that's very common, different birds in different places, or the campfire of an old man and his wife, or 2 campfires, rather. That comes in a few different cultures as well. Various other animals as well, snakes, rats, and other bits and pieces. So different groups have very different ideas about what they consider these two objects to be. If we take a look at the map now to get an idea of where you can actually see these. So in principle, you can see them from anything below about 20 degrees north. That's kind of where my line is here, but actually they're very, very difficult because they sit right on the horizon. And so they become very blurry at that height because of the Earth's atmosphere. So really they're much better seen below the equator here, and best seen below this line, 30 degrees south. So that's of course where we are in New Zealand. And from here they sit in the sky the whole time. You can always see them. Higher up in this, say this part of Africa, or higher in South America, you'll see them well at some parts of the year, and as they rotate down, you'll see them less well. So the kind of further south we go, essentially, the more important they are to various cultures because they're seen more often, a more permanent feature of the sky. So there are some parts of Africa. Now, of course, Africa is probably the most dense cultural continent. There's literally hundreds of languages and different cultures and hugely long histories among astronomy in the sky as well, but much of it is not necessarily known or not written down or maybe lost to time. So we don't have a lot of resources that tell us what people believed. But again, some of the things we know is pairs of animals tend to be very, very common. So in South Africa, we have pairs of steenbok, which are a kind of small gazelle, and some other people believed lion's testicles, which I find kind of funny as well. So again, this theme of animals is quite common. In South America, we have a few other things. Again, animals is quite common, or pools of water where animals are drinking from. That appears in a couple of different stories. And there's, for those of you that know the Southern Hemisphere sky, there's what we call a dark nebula next to the Southern Cross, which looks like a dark patch in the sky. And it's similar in size to the Magellanic clouds. Not really similar on what it really is, but just when you look at the sky, they look kind of similar. So the three are often connected together. So one of the stories that come from South America is that there was originally three pools. One of them is dried up, and that's the dark one. One of them is drying up, and that's the small Magellanic cloud. And the other one is still full, and that's the large Magellanic cloud. What they believed was once they're all empty, that is when the universe will end. So we're partway there, I suppose, about halfway. But again, there's very many, and many more that we are probably lost to time now, sadly. But we try and preserve as much as we can. Work has been done certainly in this country to write down and keep hold of what the Maori believed, and the same similar is happening in Australia. So hopefully we can preserve some of these stories and maybe uncover other ones that we don't know. But that's a kind of, I suppose, a brief overview, because as I said, there's very many different stories. So let's then go to the Northern Hemisphere. So, in fact, I'll go back one thing here first, is that the first people I'm going to talk about are the Arabs. So if we look at the Arabian Peninsula here, we find right at the very southern part of the Arabian Peninsula, that's somewhere around 10-ish degrees north. So just about where you can just see them right on the horizon if your eyesight is very, very good and you have a perfectly clear night. So the first written mention comes from the Arabs in the Islamic Golden Age. So in 964, a guy called Al-Sufi, he wrote a book of fixed stars. That's what he called them. Now, he didn't actually see these himself. So he's relying on reports from other people. And they called it the Great White Ox, which we believe is probably the Large Magellanic Cloud, although we don't know for sure because it's a second-hand account. But we think it's reasonably likely that this is the first written evidence that we have of the Large Magellanic Clouds, so in 964. Now, as I said, Europeans didn't really come down into the Southern Hemisphere properly for quite a while after that, because it wasn't until we developed much better navigational technology that people dared to do so, essentially, or at least maybe that's when people started coming back. So the first first Europeans probably to see the Magellanic Clouds would have been the Portuguese, who were the first peoples to sail down that far. But they didn't actually write about it. So whether the reports are just lost or whether they thought it wasn't really worth talking about, but they certainly did. In 1497, Vasco da Gama, one of his expeditions, did come all the way down around the Cape of Good Hope, right at the southern tip of South Africa. And you certainly can see them from there. So those sailors would certainly have seen them, whether or not they wrote about them. They definitely saw them. So this is one of the early names we actually get in the Northern Hemisphere is the Clouds of the Cape, because quite a few early expeditions were going round the Cape of Good Hope, and so that's what they associated them with. So that's the earliest name we get, is Clouds of the Cape, that was used widely by sailors. Then we're going to go on to Amerigo Vespucci, probably pronouncing that fairly wrong, who is famous, of course, because they named the continents of America after him. Amerigo, America, that's where we get it from. He did a number of expeditions, and one of the ones he went to South America in 1501. And he wrote about the two Magellanic Clouds and this third dark one next to the Southern Cross. So he thought they looked kind of similar. Of course, they do, and his writings mention them. He never bothered to make a picture, though. This picture here is actually from a few years later, but 14 years later in 1515. And that's by a guy, let's get his name right here. Andrea Corsali was his name. On a trip down around the Cape of Good Hope, he drew this picture for us, which is not especially accurate, but it's not bad for the time. So once again, we have the spot above the South Pole here. This is that circle, or roughly that circle, a bit smaller, that we talk about. Our Southern Cross is here, 1, 2, 3, 4, and here is the two Magellanic Clouds, sort of drawn a bit cloudy. So we call them, of course, the Magellanic Clouds, right? So where do we get to Ferdinand Magellan? Because, of course, lots of people have seen them by this time. The thing is, people didn't write that much about them, and we think that's likely because they weren't much use as navigational aids. So mostly what people were talking about with the stars at that time was ways to navigate around in the Southern Hemisphere using the stars. So what I mean is that in the Northern Hemisphere, people were very used to using the North Star for navigating. That's because the North Star sits pretty close to that spot above the North Pole. So if you can identify the North Star, then you found north. And you can use it to tell you how close to the North Pole you are. It's very useful. So people wanted to find something similar. They wanted to find that spot above the South Pole and use the stars to navigate in that way. Because much like we can't see the Magellanic Clouds in the north, we cannot see the North Star here. It's hidden by the Earth. And so what they were writing about was ways to navigate with the stars. The thing is, you have to be extremely accurate. So a mistake of even 1 degree in the sky, which is sort of, see, a degree is probably about this much in the sky, would be something like 100 kilometers navigational error. Right, so if you make a tiny mistake in the sky, you could miss whatever island you're looking for by 100 kilometers. And you can only really you can't see 100 kilometers at sea from a boat. So if you're 100 kilometers off, you have no idea where you are, right? You're totally lost. So a kind of big amorphous cloud in the sky is not much use for navigating because it's way too big, right? You can't get an exact fix on it. So they were talking mostly about stars. So that's why we don't really have a lot of mentions of them, that we can assume that people saw them. They just didn't bother to write about them too much. So Ferdinand Magellan, of course, very, very famous explorer. His expedition was the first to make it all the way around the world. Not him, actually, he didn't make it back, but some people, a very small number of people in his expedition did make it back. That was in 1519 they set off. And a number of things were named after him posthumously. So the Straits of Magellan, which is off the south coast of South America, for example. And he did make passing reference of the Magellanic Clouds in his notes. He didn't name them that. right? Actually, he wasn't maybe quite that egotistical, but he did make passing mention of them. Interestingly, it wasn't until quite a lot later they started to be named after him. It wasn't straight away. They were still called the Clouds of the Cape by most sailors for quite a while, and early astronomers started to refer to them as Nubecula Major and Nubecula Minor, so which is essentially Latin for big cloud and small cloud. And most science was done in Latin for quite a long time, so they just continued to name them that, all in scientific terms, all the way up until about the start of the 20th century. They start to appear in more drawings, so we've got kind of 16th and 17th century drawings of the southern night sky, so they're a little bit hard to read here, but again, this is our spot above the South Pole in this one from 1731, and we have our large Magellanic Cloud here and our small Magellanic Cloud there. We've got Nubecula Minor and Nubecula Major, which is upside down. And these are drawings of the other constellations around. And then in 1603, we have maybe a slightly better one. Again, there's our spot above the South Pole here, and our large Magellanic Cloud is there, and our small one is there. So people were certainly aware of them, right? But these, of course, are named all in Latin here. So it was really more like kind of 17th and 18th centuries they started to get this name, the Magellanic Clouds. And it was from sailors. So it just started off sailors referring to them that way for a couple of hundred years, while scientists were still sticking to their Nubecula Major and Nubecula Minor. And it was really all like that all the way up until, as I said, the start of the 20th century, when scientists stopped writing in Latin the whole time, which is good for us to understand it. And so in scientific literature, that's when we start to get Magellanic Clouds becoming accepted generally. And so it's really only about the last 100 years that everybody's been calling them the Magellanic Clouds more generally, despite Magellan doing his expedition about 500 years ago. So I think it's kind of interesting, that history. You assume that these are named by Magellan or straight after him, but it really was a much slower kind of process to what we've got now. We quite often abbreviate them now because large Magellanic Cloud can be quite hard to say and write down. So we quite often call them the LMC and the SMC. So they might have referred to them sometimes going on like that. There's one other piece of history, though, which I think is worth mentioning, which is Henrietta Swan Leavitt. So she was an astronomer working in the early 20th century. And a lot of the early astronomers were women, and a lot of them don't really get a proper recognition, I think, so it's worth mentioning here. Because what her contribution was extremely important, and was using these Magellanic Clouds. So without getting too technical, let's see if I can explain it. Some stars vary in brightness. And some of them do so very predictably. So over a certain period, this is a certain kind of star we call a Cepheid variable. Cepheid just coming from the first star that was identified that did that. And it was noticed, these stars vary very predictably. Say this one over 5.4 days in brightness, up and down. They just keep doing that. Very, very stable kind of oscillation between brighter and less bright. And what Henrietta Swan Leavitt did was look at the small Magellanic Cloud and found some of these Cepheid variables. Now, her kind of leap of imagination here was that we don't know how far away the small Magellanic Cloud is, but we can probably say all the stars in there are roughly the same distance away, probably, whatever that distance is. So the brightness of these Cepheid variable stars is, we can probably say that if you compare a couple of them, that's like a comparison between their true brightness. So what I mean is, the problem here when you look at a star is you don't know how big it is. So you don't know if it's just very big and very far away, or just very close to you in a normal size, right? You have no way of telling usually. It's very, very difficult. But if we can say all the stars in this little group are kind of the same distance away, then a brighter one is bigger, most likely. That was her thinking on that. And when she did that, she plotted it out on a graph, and she found there was a relationship between the absolute brightness, the maximum on this graph, and the period. So how long it took to go right down and right up in brightness. There's a very strong relationship between those two. Now, this is important because if you go and find another one of these stars somewhere, say in the Milky Way or in a different galaxy, then you can take this relationship and know there's a relationship between the absolute brightness and how fast it oscillates, and therefore you can come up with an estimate of how far away it really is by looking at how bright it appears to us. This is a big leap because it was a way to measure the distance to other galaxies, which had not been done before. So a really famous guy we call Edwin Hubble took this idea and found some Cepheid variables in the Andromeda galaxy, which at the time was not known to be a galaxy. They called it the Andromeda Nebula, and found it to be, on his calculations, more than 1 million light years away. We actually know it's more like about 2.5 million light years now. He wasn't that accurate, but he did realize that there was in fact another galaxy, because previously it was pretty much thought the Milky Way was the entire universe. There was other galaxies didn't exist. So this is an extremely important moment, I would say. Henrietta Swan Leavitt should maybe get more of the acclaim, in my opinion. And she used the small Magellanic Cloud to do so. So to sort of now, because our understanding in science of these Magellanic Clouds has changed significantly in even just the last 20 years. We've come up with a number of ideas which have been proved wrong several times now. So originally, in the kind of 20th century, it was thought that these are what we call satellite galaxies, so small galaxies that are orbiting around our Milky Way, and it was thought they'd been doing so for billions of years. And then in 2007, with the Hubble Space Telescope, they measured the speed that these galaxies are going at and found them to going far too fast to just be going round and round and round and round. They were going so fast they thought that they would probably just pass the Milky Way and zoom off back into interstellar space. And then a few years later, we came up with a slightly different estimate of the masses of these things and thought actually maybe they're not doing that at all. Maybe they will merge with the Milky Way later. But I'll come into more on that in more detail in a moment. We'll start with what we mean with nearby galaxies. So we've got something here we call the local group of galaxies. So this is a group of about 80 or so galaxies that are relatively near to us in the Milky Way. And what we say, they are gravitationally bound together. That means the force of gravity between all these galaxies is more powerful than other influences, and they probably are destined to sort of stay near to each other or merge together in the future. So in our local group of galaxies, we are not the biggest one in the Milky Way. Actually, it's the Andromeda galaxy here is the largest one, maybe about twice the size of our Milky Way. We're here, and we can see there's a number of small galaxies surrounding each big one. So we have, in the Milky Way, we have a whole number of these smaller satellite galaxies, the kind of Sculptor, Fornax, Carina, Leo, Canes, etc. And of course, the Magellanic Clouds here. So pretty close and actually pretty big. And Andromeda has a number of smaller ones around it as well. So if Andromeda is the biggest one, Milky Way is the second biggest one. Then this one we call Triangulum, which is relatively near to Andromeda, is the third biggest. And the fourth biggest then is the Large Magellanic Cloud. So it's actually fairly sizable in our little group of galaxies. And if I can zoom in a bit further on just our bit, we can see that they're both sizable and pretty close. This one, by the way, the Sagittarius dwarf, we think might actually be merging right now with the Milky Way galaxy. So that's kind of our local group, where we think they are in space relative to us. So kind of what actually are they themselves? I've blown up some pictures here for us to have a look at. We'll start with the Large Magellanic Cloud on the left. We, again, originally considered these to be kind of irregular dwarf galaxies. That's what they were called because there's no really obvious structure when you first look at them. But with better photography and modern techniques, it actually does seem there's a structure here. So a lot of big galaxies have these beautiful spiral patterns, and quite often they have a great big bar across the center as well. And we actually think the Large Magellanic Cloud exhibits some of this structure. We see we have a bar in the center, and it looks like we have a sort of arm, like so, and maybe the remains of a second one on the other side. So actually we now think that this was maybe a small spiral galaxy, And because it's been interacting with the Milky Way, getting too close to our galaxy, it's been disrupted, and the spiral shape has been sort of is disappearing. But we can still see the remains of it. We think a bar and maybe one spiral arm on each side. Interestingly as well, there might even be remains in the small Magellanic Cloud of a bar structure as well, although it's much harder to see visually, but we think it might be there. So we think these actually might be more classic spiral galaxies before they got a bit too close to our Milky Way. Now, this, by the way, is an object that is not associated with the small Magellanic Cloud. This is actually inside our own galaxy. It's just what we call on the same line of sight. Much, much closer to us. It just looks close to the small Magellanic Cloud in the sky, but is not associated really in any way. Of course, we see all these foreground stars. They are, again, inside our Milky Way galaxy. They're just in between us and these background galaxies. We can see also there's quite a lot of sort of stuff going on in the Large Magellanic Cloud. There's quite a lot of action and things happening in there. These galaxies seem to be have lots and lots of gas in them. So hydrogen gas, which contributes to lots of star formation. They seem to be quite active as galaxies go. Not all galaxies are. Some galaxies are really not active, not producing new stars at all. Our Milky Way is producing a reasonable amount of stars, not as much as some other galaxies, but certainly still quite a lot of stars being produced. So let's see. Now, in the 1970s, we started to use what we call radio telescopes. So looking in frequencies of light that are not the same as that we see with. We used the idea with your radio set that's sending wireless signals through the air. So we can use these same frequencies of light and great big radio telescopes to see things that are not visible with our eyes. And this is a kind of view of the whole sky, just kind of turned into an oval shape, like you might do with a map of the world, for example. We can see our Milky Way is in the middle here. The Magellanic Clouds are there. And we see this great big kind of stream shape, and we call it the Magellanic stream. Detected in the 1970s. It took them a bit longer to work out what it actually was, 'cause it's actually quite hard. You see something, it's difficult to work out how far away it actually is and how big it really is. Is it just close to us, or is it far away and very large? And it turns out this is a kind of big stream of gas that is sort of wrapping around the Milky Way. And it seems to follow the path that the Magellanic Clouds have taken as they have approached the Milky Way. So the current thinking is that these Magellanic Clouds maybe come from deeper space, and they're either making their first way around the Milky Way or maybe second way around the Milky Way. Still a lot of debate about that. And this is the sort of path that they've taken. And because of the way the gravitational dynamics work, you get a little bit sticking out in the front in the direction they're going as well. So this is a kind of very faint hydrogen gas that we are seeing that kind of gives us a clue about where they've come from. So that was detected in the 1970s. Much more recently, we've detected a whole lot of gas linking these two galaxies together. We call this one the Magellanic Bridge. So this kind of glow here is like, again, gas that exists between the galaxies. What this suggests is that these two Magellanic Clouds have been interacting through gravity before they approached the Milky Way, and we get this sort of bridge of stuff between them, which we found gas originally, and in the last few years we even found stars in there. So if we, slightly different view here, we do it like this. Now, once again, these are our two galaxies, and the stars have sort of different colors in here, and we see this little group. This is what the interesting part of this image, which is a group of very large stars that seem to be sort of leaving the small Magellanic Cloud, heading along that bridge towards the large Magellanic Cloud. So it suggests maybe that the small Magellanic Cloud is actually being kind of torn apart a bit. So stuff is being stolen, gas and stars are sort of being stolen from the small Magellanic Cloud into the big one. And yet another team actually did a slightly different visualization of the same thing. So again, we've got a small Magellanic Cloud here. These arrows are particularly large stars in the direction that they're going. So the large Magellanic Cloud would be off the bottom left here. That's where that is. And we can see this is again that sort of bridge, and these stars are moving really quite fast out of this galaxy, and there's really quite a lot of them. So this team suggested that the small Magellanic Cloud is actually being ripped apart. We're not totally sure whether that's true or not, but that's possibly the case. So there's a lot of dynamics between the two, right? They seem to have been interacting for a long time before they approached the Milky Way, and potentially they will merge together in the future. That's a bit difficult to really say for sure. And so we think that the Magellanic Clouds, as a pair, had their closest approach with the Milky Way something like 2 billion years ago. So they're actually heading away from us now. So they came close maybe 2 billion years ago, have made a close pass with the Milky Way, and maybe zooming off in the other direction now. And so if we now, there's one other thing on this one, which is we're pretty sure the large Magellanic Cloud has an extremely large black hole in there. We call this a supermassive black hole, and that's what this abbreviation is here, supermassive black hole. And the way that we've found this, I think, is very clever, personally. We find things that are called hypervelocity stars. So these are stars that are going so fast that they can actually completely leave the galaxy that they seem to be part of. So we find these stars going incredibly fast. We thinking about how this could possibly happen, how a star could be accelerated really that much, the main way it would happen would be from getting too close to one of these extremely large black holes. So the way this works is we've got two stars here, first of all. So we call these binary systems, so stars that orbit around each other. Our sun is not a binary system, right? We only have one star. But lots of other systems are two stars together. So these two stars are orbiting around each other quite happily, and the pair of them are moving through space together, and they move towards an extremely large black hole, and they get close to it. And then sometimes what happens is one of the pair gets pulled off and into a close orbit around the big black hole. And what that happens to the other one then is it gets a huge gravitational kick and gets sent off in kind of the same direction it was going, but much faster. It gets blasted straight out of the galaxy. So by analyzing a whole bunch of these hypervelocity stars, we think they come from the Large Magellanic Cloud, and we think there's a black hole with something like 600,000 times the mass of the sun in there. We haven't directly imaged it or anything yet. We're just using this method. We think it's most likely there. So that's kind of where we are on the science of them at the moment. That could be subject to change, right? It has changed a lot over the last few years. But now we kind of be a bit more speculative and look at where they might actually be going, like what's actually happening with these things. So the first thing I want to talk about is something we call a galactic halo, because we think of galaxies as being like these little things here. But actually, there's a whole lot more to galaxies. So this is actually the Andromeda Galaxy, or that other member of our local group. So it's kind of that size normally, but actually if we carefully map out lots and lots of kind of very faint, very diffuse gas around the galaxy, we actually find an enormous halo, much bigger than what we think of as the galaxy itself. And this is very spread out gas, but extremely hot. So very energetic little particles zooming around in this huge halo around the galaxy. Now this is important because these Magellanic Clouds are fully inside the Milky Way's halo. So even though they're about sort of 100 to 200,000 light years away from us, they are interacting with our galaxy already. Whether they might merge in the future as well, but they're already sort of merging and already colliding. Now it's very hard to see this halo, right? So it's so diffuse, it's not really producing very much. We have to use other methods to kind of work out it's there. One of the ways we do it, this is a bit of an artistic rendition here, is we look at very far away, extremely bright points of light, essentially, we call quasars. And we look kind of next to something like this, the Large Magellanic Cloud. We can infer that there's hot gas there, looking very closely at the spectrum of light. So we've done this for the Andromeda Galaxy, that's how we got that picture before. We've tried to do it for the Large Magellanic Cloud here. So what we find when we do this is the Large Magellanic Cloud has a halo as well, but it's only about 10% of the size we would expect for a galaxy of that size. So what seems to have been happening as these clouds come towards the Milky Way is all this halo, all this gas and dust is being kind of blown off by the Milky Way's halo. So it's losing gas at a huge rate as it's got too close. So although the halo still exists, it's much, much smaller than how it started. And this is possibly how that Magellanic stream has been forming, right, as these galaxies go through. If there was no halo left at all, what would happen is all the stuff of the galaxy would be ripped off instead. And this has happened to most of the other small satellite galaxies near the Milky Way. So the other satellite galaxies we look at, they have no gas and dust in there. They're not producing new stars because it's all been stripped out by our Milky Way. The Large Magellanic Cloud still retains some of its halo, so that's how it's still producing new stars. There's still gas and dust inside the galaxy itself, so it's still protected a bit by this halo. But because it's already been at its closest approach, it'll probably retain that 10%, at least until maybe it comes closer again in the distant future. So it'll probably still produce stars for several billion years into the future. So where are we going from here? Oh yeah, so this is, if there's kind of broadly a couple of scenarios what might happen. The Magellanic Clouds might merge with the Milky Way. And this is one image we have here. This is what we call the Whirlpool Galaxy, which is a galaxy not dissimilar to the Milky Way and a small dwarf kind of galaxy like the Magellanic Cloud that seems to be merging with it. So this might be the future in one way. It might also be that the Magellanic Clouds are still going so fast they'll fully escape the Milky Way's gravity. The problem is we don't know exactly how much all these galaxies weigh, how big they really are. So we're getting closer. Over the years, we've come up with different ideas. We can go and count all the stars and the gas and the dust in them, but actually there's huge amounts of stuff that we cannot see. We call it dark matter. We're pretty sure it's there. We just have not found it yet at all. But we're pretty sure all galaxies have significant amounts of this dark matter that we can't see that is there, much more by weight of all the stars and all the gas put together. So most of the stuff of a galaxy is actually completely invisible to us. It seems that way. So it's actually quite hard to measure it, right? Exactly how much is there. So different ideas have been put forward over the years, and we've been revising up in recent years. So we now think the Milky Way is much heavier than we originally thought. We also think the Large Magellanic Cloud is much heavier than we originally thought, and that changes what we think will happen in the future. So now, I've got a couple of graphs here. I'll try and stick with me a little bit. This is a simulation that was run in 2019. And the problem with simulations, when you're simulating huge volumes of stars and gas and dust, is even today's supercomputers struggle, right? There's just so much stuff there. So this was done in 2019. So on the bottom, we have time from today in billion years. So that's 1 billion, 2 billion, 3 billion years, etc. And up the side, we have distance from the Milky Way. So at the bottom there, that is hitting the Milky Way. And then further up there is kind of tens or hundreds of thousands of light years away from the Milky Way. So we have the Magellanic Clouds in blue and Andromeda in orange. Because if we're projecting into the future, we need to think about what Andromeda is doing as well. It seems Andromeda is coming directly towards the Milky Way, and we'll maybe get here in about 4 or 5 billion years' time. But that means that if we're running predictions into the future, we need to factor that in as well, because it's going to have a really big impact on what happens in a few billion years. You can't just consider isolated little parts of the system. You kind of have to consider the whole of that local group of galaxies. But that's way too computationally difficult. So usually we just look at a few of them. This one just looked at 3. So our galaxy, Andromeda, and the Large Magellanic Cloud. Just computing power constraints, really. So what we get with our best guess of the Large Magellanic Cloud's weight, we're not really that sure about it. We said we've not directly measured it. It's just coming from when we run simulations and we kind of what we think is most likely. We get that it comes, so it starts off about here, that's where it is now, and then it's moving away from us, and then it will sort of turn around, stop, and come back towards us, come very, very close, move away again, and then eventually merge in maybe about 2.5 billion years' time. But if it was much lighter, kind of at the lower end of what we think it might be in weight, it won't do that at all. It'll move away from us and then slowly start coming towards us. But by that time, Andromeda's coming towards us. And so it interacts with Andromeda coming in as well. So what might actually happen is it would be bumped completely out of the system, kind of given a huge kick by Andromeda's gravity. So it completely depends on the weight of our galaxy in the Large Magellanic Cloud, whether it will merge or whether it will just be blasted off back into deep space. Or it's a very kind of complicated system, so maybe all of them would merge at a later date as well. It's kind of hard to say. I have one other one which is a little bit more confusing here, so sorry about that, which is a more recent one done, a simulation involving 4 galaxies this time: the Milky Way, Andromeda, the Large Magellanic Cloud, and that Triangulum galaxy, the 3rd largest in the group. What we find is that anything could happen. Well, if you sort of, the one that we're most interested in is the top right one here. So these are different scenarios. These lines are different scenarios with slightly different initial conditions, different weights, slightly different sort of velocities as well. And the other 3 are just different combinations. So just the Milky Way and Andromeda is that one. Just the Milky Way, Andromeda, and Triangulum is that one. And then just the Milky Way, Andromeda, and Large Magellanic Cloud is this one. That's most similar to the last simulation that I showed you, this one. So even just between the 2, Milky Way and Andromeda, there's quite a lot of scenarios where they don't even hit each other at all. They just kind of get close and zoom off back into deep space. The black line is what we think most likely, probably. And any time a line hits the bottom, that's when they're merging. So when we sort of, and this number here is the percentage of scenarios in which they merge. So just consider the 2, only 44% of the time they merge if you run all these different scenarios. If you consider all 4, then about 54% of the time in these scenarios they merge. So it's marginally, we think, most likely that all 3 are going to merge, but like any small change in those conditions could mean that they won't at all into the future. So it's sort of very speculative, right, all of this, because there's so much we don't know. And also, there's no real way of kind of testing it. Right? We cannot actually just transport ourselves forward 5 billion years in time and see what happened for real. So in a way, it's kind of, if you can't test predictions in physics, a lot of physicists just think it's kind of worthless and pointless to actually even start. But people are still interested. We still want to know what's going to happen with the universe. So even though it's kind of extremely speculative, it's still, I think it's still interesting. But the bottom line is we don't really know. Most likely, will merge together. But one interesting scenario of all this is that maybe the Milky Way and the Large Magellanic Cloud will merge in maybe 2.5, 3 billion years' time. And that will actually kick the Milky Way out of the path of Andromeda. So cause Milky Way and Andromeda not to merge, perhaps. So, because we used to think it was pretty like, very, very, very likely the Milky Way and Andromeda would merge together. But when we consider some of the other galaxies interacting, we think, maybe not. But that's kind of state. Maybe we'll come up with some better ways of measuring in the future. We shall see. So the final thing I want to mention is a few interesting features about these galaxies. I think we still have time. Yeah, we're doing good. So the first one is something we call the Tarantula Nebula, which is a fan favorite around here, or staff favorite with us here, the Tarantula Nebula. So this is our Large Magellanic Cloud, and we see this kind of bright spot there. This is a huge area of star formation. So lots and lots and lots of stars forming just now. It's actually the largest area of star formation in the whole local group, right? Extremely active. And if we kind of zoom in a little bit, this one, we can see this shape that some people think looks like a spider or a spider's web, which is where we call it the Tarantula Nebula. And there's a whole bunch of like huge volumes of stars in there, right? Kind of hundreds of thousands of stars possibly in there forming at the moment. And it's all these young stars in there that cause this stuff to glow. This is mostly gas and dust, hydrogen gas and a few other things. And it's glowing like that because those extremely active stars in there are producing lots and lots of ultraviolet light, which is the same kind of light that gives me a sunburn, anyway, which causes the gas to glow like this. And so if we then look more closely at that central section, we get a cluster, extremely large and active cluster. There's something, we estimate the mass of this cluster in there, maybe about 450,000 times the mass of our sun in stars. It's very, very new. So we think, well, the way it works with these clusters is typically the largest stars in there die pretty fast within a few million years. This one is so new, we think none of them had died yet. So this is almost like a pristine kind of cluster in a way. And in there, right in the center, we actually find the largest star that we have so far found in the universe, which is, if I remember my numbers rightly, about 250 times the mass of the sun, something like that, which is just about as big as we think a star possibly can be, right? So we've got and several other extremely large stars in there. This is such a big cluster as to be very, very interesting. Like, we don't find clusters of this size forming in the Milky Way, really. And what the kind of thinking on this is, as the Magellanic Cloud has been approaching the Milky Way through that galactic halo, all the leading edge is being sort of compressed. And it's this compression which is causing huge amounts of star formation. We call it a star burst zone. It's caused just by that huge compression. It wouldn't just happen by itself, it's only because it's moving through the Milky Way's halo. So that's our Tarantula Nebula. Now there's another one. This is the only supernova we've seen nearby to us since we invented telescopes. So a supernova is the death of an extremely large star. The biggest stars, the really, really big ones, when they die, they explode extremely violently. So violently we can see them from across the universe. So we can see supernova in almost every galaxy we can see, because they're just that bright. There hasn't been one inside our own galaxy since 1604, actually. We invented the telescope in 1609, annoyingly, ironically, you might say. We haven't had any since then. But in 1987, there was a supernova inside the Large Magellanic Cloud, and it was visible with the naked eye. It wasn't that bright, but it was like a new star that had appeared in there. And this is important because, as I said, it's by far the closest one to us that we have seen in modern times, into 1987. So we have kind of three images. The first one is before it happened, and this arrow pointing to the star that would blow itself up. This is when it was happening in 1987. We see it suddenly become extremely, extremely bright, and it stayed at that brightness maybe for a month or something. And then this one is taken by the Hubble Space Telescope a few years ago, which shows the aftermath here. We see these interesting, like, various ring shapes there, which is the sort of aftermath of this explosion. So the star that died is in the center here, and then these rings, well, I'll show you where these rings we think come from. This is a sort of various images taken by Hubble Space Telescope over a few years. So Hubble Space Telescope only came online in 1990, right? So 3 years after it happened. So we couldn't watch it happening with Hubble, we could only watch the aftermath. No other telescopes really have had the resolution to see it in this detail. So what we have is, so 1994, a few years after it happened, this is the sort of remains of the star that's expanding outwards. This ring around it we think existed for maybe about 20,000 years before that, and it's kind of, we think it's probably bits of the star that came off as it became very unstable towards the end of its life, and creating this big ring shape, which is being lit up, because when the supernova went off, it created lots of this ultraviolet light, which caused this ring to start to glow. So it wasn't visible before, only after the supernova. And then a few years later, we see, well, this bright spot, by the way, is a star in the foreground. That's nothing to do with this image, so we can ignore that one. We see in 1998, it's starting to get sort of brighter. And then 2003, the whole thing started to light up. So what's happened here is the shock wave from that supernova has then hit that ring, that already existing ring. And it causes it to light up in this really beautiful way. And it sort of got brighter over the intervening years, and then about 2016 it started to get less bright as the shockwave passed by that ring and kept going. So again, this is kind of detail that you just do not get on other supernova at all. So it's actually this 1987 supernova has informed our kind of theories and our thinking about how the biggest stars die, just because we've had that chance to study it in so much more detail. And we have a little animation here. This is a simulation, really. That's the supernova going off. That's the existing ring. We see the shockwave kind of heading out and hitting it. This is pretty much what we think probably happened. So this is a simulation, not actually a real image. But we can see the kind of the halo keeping on going. And actually, in future years, it'll be very interesting to see if anything else happens with this shockwave as it keeps propagating out, because it will keep going and going and going and going for thousands of years, actually, just because it's so high energy being blasted away from that initial star. And finally, then, one last thing, which is, well, for a lot of stars, this is something we call a globular cluster. So I know that's a bit technical term, but what that means is an extremely large cluster of stars. So these are in the region of kind of hundreds of thousands We find them all around galaxies. We find about 159 of them around the Milky Way, and they're all really, really old. So all the ones in the Milky Way are in the region of at least 5 to sort of 13 billion years old. No new ones at all. We think they have something probably to do with the formation of galaxies, but we don't yet fully understand them. There's so many stars in this group that they are kind of stuck together in a giant ball. That's where we get the word globular. It comes from Latin, just globe-shaped. I think they'll spread out over time, but these ones do not. The thing that's special about this one is it's pretty young. It's probably only about 1.7 billion years old. Now, if you remember that the Large Magellanic Cloud approached the Milky Way maybe about 2 billion years ago, this was formed when the Large Magellanic Cloud was just about at its closest approach to our galaxy. That's what we think. So we can look at these little galaxies and see events happening that haven't happened for billions and billions and billions of years around our galaxy. It's almost like a kind of window back into the past. In that way, we can look at how these globulars form. And if we go back to that Tarantula Nebula, the first one I showed you, some scientists think that might be a globular cluster forming. We're not totally sure yet. We have to wait a few billion years maybe to see. But yeah, it's really interesting because to be able to observe that at a close distance. The only other way we can see these globular clusters forming is by looking into the extremely deep past in very, very deep space, very, very, very far away from us. And you don't get that kind of resolution at that distance. You can't see all these beautiful stars. Well, that's right on time. So yeah, that is the end of what I wanted to explain to you guys. I hope it all made sense. Your brains are not melting too much. So yeah, if you've got any questions, I do love questions, so please don't hesitate.
Sorry.
Yes. So it is, if we go back a few steps, so we have a picture, this one. It's about here actually. So on the opposite side to the Tarantula Nebula. Remember I said this is the kind of the front? Well, that would have been the front when it was approaching the Milky Way. And as it's gone past, then this is now the front. It's in the direction of motion, if that makes sense. Like if you imagine my laser pointer coming towards the Milky Way, that's the front, comes around, and now that's the front. So it was at the shock front in the first place as it was approaching. Yeah, question over there.
Will there be more and more stars in the Milky Way, or will some of them be kicked off or go together?
Sorry, ask the question again.
Will there be more and more stars in the Milky Way?
Yeah, so the Milky Way is producing lots of new stars all the time, yeah. And if these galaxies do merge together, our Milky Way and the Magellanic Clouds, it will trigger a lot more star formation, huge amounts of star formation. It might also, so our Milky Way also has an extremely large black hole in the center, much, much bigger again. If these galaxies merge together, what might happen is it will suddenly sort of wake up. So it's what we call, it's being quiet at the moment, it's not doing very much, but if the galaxies merge together, then it will suddenly start to consume lots and lots of stars and gas and dust, and become something we call a quasar. So become very, very active and shoot huge beams of radiation into space and then grow in mass, maybe up to 8 times, potentially. So, although we do have a lot of star formation now, if the galaxies merge, it will be much, 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 much more. Cool. Yes, Olive.
For the supernova, do we know what was left behind in the middle?
So we have been looking at it, yeah. The predictions were that there would be a neutron star in the center, but up until very recently, we hadn't found anything. All that kind of gas and dust in the middle was too dense. A recent analysis of it suggests, yeah, thank you guys, there's certain elements that are being lit up, or certain molecules that are being lit up by whatever's in the center, which very strongly suggests it's a neutron star in there. So although we haven't pinpointed it directly, indirectly we think it's there, yeah.
I have a question.
Yeah.
I remember last year there's a research by a bunch of astronomers that they suggested the large cloud of Magellan might be 2 galaxies instead of 1.
Ah, yes.
They found like 2 different populations of different age, different metallicity. Is there any more study towards that? Do you think it is just because the field of view they were looking at?
So it's a small Magellanic Cloud. And yeah, what they found when they looked at it was it might be 2 galaxies right behind each other. Or potentially the small Magellanic Cloud has been sort of ripped in half. That's another interpretation. There hasn't been any new studies as far as I know. That one's fairly fresh. What they found was there seems to be about 20,000 light years between two different groups. A kind of big, these star-forming areas, these nebulae, two distinct kind of groups quite far apart with different kind of chemical compositions, which suggests they might have been spread out for quite a long time. Being one right behind the other, it's actually very hard to tell. We cannot just go to the side and have a look, because we'd have to travel 100,000 light years to do that. Not really possible. But I assume there'll be more studies on that coming up, but it'll probably take a while for them to produce anything. That's quite a kind of fresh finding, that one.
Except it was like that black hole in the middle of it in the Milky Way. Is there any way we can see where it possibly is?
Yeah, we have actually found it, and we have actually directly imaged it as well. So what was done originally was over about 16 years from the late 90s to early 2000s. We looked very closely at movements of stars right in the center of the galaxy. So there's huge volumes of stars in the middle of the galaxy, and some right in the middle were doing extremely strange things. So they're orbiting on very tight, very fast orbits around nothing, right? Just nothing at all. There's just nothing there, seemingly, and these stars doing really tight orbits around. And using a bit of maths, called Kepler's laws, if we see stars doing that, we can actually estimate the mass of whatever's in the middle. It could by analysing the orbits. What we came up with was something in the region of 3 or 4 million times the mass of the sun in the centre there, invisible. So that was done first, and then a few years ago, we actually directly imaged this thing. So they've very blurry, but you can actually see this black hole with a kind of disk of super hot material orbiting around it. So we now know for sure it's there.
How will that affect the Earth? What's left of the Earth?
Oh, I mean, it's not going to affect the Earth in any meaningful way, but unlikely. If it becomes active and starts spewing out lots of radiation, if we're very unlucky, we might be sort of affected by that, but probably not, because it will fire radiation out, kind of, if you imagine the disk of the galaxy this way, fire up and down the way. So we're probably not in the path of it, probably. So okay. Awesome. Okay, so thanks very much for the great questions, guys.